Civil engineering is often described as conservative, slow to adopt new technology. In the case of HPC, that is high performance computing, that criticism seems justified. If we take a look at other disciplines such as aerospace or mechanical engineering, th- those guys are running massive simulations to support some of their critical decisions. While civil engineering often seems content with if it's code compliant, it's enough. The real story of how HPC is going into the discipline of civil engineering and what will happen in the next years is more subtle. HPC is entering civil engineering, however, not in the way many people expect. On paper, civil engineering is perfect for HPC. I mean, think about it. We deal with nonlinear materials, extreme uncertainty, very long lifespans that we have to design for, and rare but very catastrophic events. And we expect the systems to perform and not fail with very small probabilities. And then the systems that we design, they're impossible to test at full scale. And yet, most real civil engineering projects still rely for the design on linear models or outdated methods such as response spectral analysis or simplified checks that run on top of laptops running Excel. So why hasn't HPC become central to the practice of civil engineering still in the year 2025? There are at least three reasons I can think of for this. The first one is economics. Civil engineering runs on tight margins. The clients don't want to pay 10,000 CPU hours to run massive simulations if a code compliant design is enough to satisfy a contract. On the other hand, the other reason is codes and liability. Building codes institutionalize simplified modeling, and the courts understand these models, so engineers are rarely rewarded and often penalized for using advanced computational methods. And third, and probably the most important roadblock, is that our problems are highly heterogeneous. Every site, every soil profile, every structure is unique. That makes it hard to reuse simulations in a way that aerospace really reuses, for example, wind models or flow solvers. Reusability is key. And reusability in civil engineering is going to be there, but it's going to occur in a different way. Now, the uncomfortable truth is that HPC does exist in civil engineering, but it's restricted mostly to academia, such as myself, national labs, and a handful of specialized consultancies. It's disconnected from day to day design and treated as a research item rather than part of the regular engineering design infrastructure. Its principal issue is not computational power. The computational power is there. The key issue is integration into decisions that matter. There's this false dichotomy or a false narrative running around that large and complex finite elements are not useful, that the future is reduced model surrogates and fast simulations. If you look at the trend of engineering research, we've been trying to do simplified modeling and nowadays surrogate modeling for the past years. Now, it's only half true that this is the case. The future of civil engineering actually might not be big models or small models. It's going to be, in my view, big models feeding small ones in a tightly coupled workflow to resolve the usability issue. Now, large complex models are still needed nowadays, and more so in the context of performance-based engineering design, which is what the industry is pushing for, at least in terms of research and in terms of what is spoken at the conferences. Large, high fidelity models are the only place where we can have any hope of expressing the full physics involved in producing a structural response. If you care about nonlinear soil or structural behavior, if you care about wave propagation from source to site, wave passage effects, if you care about surface waves, if you care about fluid structure interaction, soil structure interaction, if you care about chemical attacks to structures, if you care about interaction between structural and non-structural components, or maybe advanced devices for energy dissipation, If you care about building stuff that's not on Earth, then at some point you're going to need the full model. In my own research, I've been looking at how advanced modeling compared to lower fidelity modeling feeds into what we see as uncertainty in our response predictions. I use very large finite element models of structures and advanced earthquake input methods such as the domain reduction method to test the hypotheses and see which way the uncertainty shifts when you make an assumption or another. In consulting, I've had to use very large finite element models for analyzing the stability of concrete face rockfill dams, where the geometry, materials, and the boundary conditions just force you into very large nonlinear models that will run for weeks. So HPC actually enables engineering, and HPC doesn't just make these models possible. With HPC, you can make this modeling systematic, and that's the key issue here. Instead of having one heroic analysis that it's meant to cover all the bases, you can use several models to explore, to figure out what your uncertainty is. And that's one of the key aspects of civil engineering moving forward. What happens if your stiffness degrades faster? What happens if your motions are spatially variable? Is your response sensitive to this? What are your drainage assumptions? What happens if your constitutive model is modeled this way or another way, or is there's high uncertainty in one of the parameters? So parametric sweeps or explorations of the uncertainty space are going to be a huge part of the practice of engineering simulation for civil engineering moving forward, as long as computationally we're there to deal with that. So performance-based engineering is going to evolve not into just simply performance-based earthquake engineering, but PBEE is going to stand for physics-based earthquake engineering moving forward. At least that's the direction I want to move into. So we want to model the whole phenomena, the full physics, from the rupture at the source to the wave propagation through the crust, to model basin effects, to model nonlinear side effects, to model soil structure interaction, and all types of nonlinear couplings between the site and the structure. And we want to, in detail, see what happens at the structural component level and non-structural component level, because we care about fragilities. And to compute fragilities, we have to do this not once, but several times. This chain of simulation is not tractable without HPC. And when I talk about HPC, I mean not just simulation, several simulations. I mean simplified models. I mean the whole deal. Now, and this is critical. This is not a simulation chain that we're gonna run every single day. But we want to leverage reusability. The way I see large models playing out in this scenario is using large models as training grounds. Large models are gonna feed reduced order models, AI-based macro element models or surrogate models, and they're also gonna feed digital twins that run in real time. But we don't need AI to replace physics. We need AI to distill physics so we can reuse, so we can do reusability in civil engineering. This is where we're moving. So over the next 25 years in civil engineering, we will move towards continuously updated digital twins, sensor-informed models, physics-trained surrogates, and HPC-backed risk engines. Um, Large models will sit at the top of this modeling hierarchy, and the expensive, sorry, but the cheaper fast models will sit at the bottom, informed by the large models, which are gonna lead into cheap, adaptive, and operational systems with which we can do design. Now, this isn't about building better buildings or safer dams. As we design infrastructure in more extreme environments, in offshore, Arctic, underground, or even off planet, we're gonna further lose the luxury of empirical design. In these contexts, physics plus computation are going to become the code. When I look ahead, I see the next 25 years of my own career as a teacher, researcher, and a consultant working to bring about some of this change. But this endeavor is far bigger than me or any single person or any single group. If this vision resonates with you, you're invited to be part of it. That might mean pursuing an advanced degree, a master's or a PhD here in Chile. I am very, very open to receiving people and working with me towards this end. Or it might mean collaborating in other ways, such as research, consulting, open source work, or shared projects. Uh, might I add, I believe that in this HPC vision, open source software is going to play a key role. Because one of the other things that is not scalable for civil engineering nowadays is the structure of HPC software in terms of the licensing and the cost to run. The tools are evolving, the questions we have to face are deep, and the problems, they're genuinely interesting and challenging problems worth devoting a lifetime to. In any case, this is going to be a very fun ride. I wish you tag along.